I expect there will be some additional attendees signing in, but we have a lot to talk about and certainly a lot to hear from a special guest. Uh, I'd like to welcome you all to both the June section of the NIHS Southern California Environmental Health Science Center seminar series, the culmination of the academic years series, and also a very special lecture. Today is the 2021 John Peters lecture, and I'd like to say just a few words to introduce both the lecture series and explain about the history and provide some comments for the introduction to our speaker. So let me move forward with that. The John Peters lecture is a commemoration and actually a legacy acknowledgement of the work that John Peters did as the founding director of this environmental health division, which at the time was actually initially environmental and occupational health, based on John's work. This was initially established in 1980. John was an occupational physician, done a lot of work in a number of different important areas, understanding the exposure of workers to silica, to asbestos, to vinyl chloride, was particularly interested in firefighters and their inhalation concerns, to granite workers, to auto workers, to just a whole range of occupational issues for many years in his research at Harvard, and then when he came here to USC. In the early 1990s, he also got interested in air pollution and in the potential chronic effects of air pollution in terms of breathing it day after day, year after year. And with support from the state of California, developed and led to the formation of a research team that began the Children's Health Study. And after several weeks of consideration, among other things, we came up actually with that catchy name, the Children's Health Study. And it's forever been commemorated as a CHS since that. The study began in 1992 and continues on in some form through this very day. A number of spin-off studies, really a family of studies, initially hosted by the state of California in terms of funding, and then provided primarily since then by the National Institutes of Health. So I want to acknowledge the funding sources in addition to some additional important funding by the U.S. Environmental Protection Agency and the Hastings Foundation to allow us to do much of the different spin-off studies. After John's death, the sense cumulatively was that, his work, his legacy, we want to acknowledge the importance of what had been done and continue on. And so he began the John Peters Lectureship. The inaugural lecture was in 2014 and delivered by Jim Merchant, from the University of Iowa, who was a close friend of John's. He was introduced at that time by Tom Smith, shown in the picture here in the lower left, also a close friend of John's. Jim was the founding dean of the University of Iowa School of Public Health, also was a very important participant, player, advisor to us here at USC in terms of our NHS Center, had continued to played a role, important role in terms of leading the Health Effects Institute Research Committee, and in terms of his own seminal work in research as an occupational physician, had contributed in very important ways to establishment of the OSHA National Cotton Dust Standard, and went on to study provide a number of important insights into rural and urban asthma through the course of his career. In fact, Jim was originally planning to be here to make the introduction of Bert Brunekreef, but last minute change of plans and made it not possible for him to attend. So I'm a poor substitute for Jim Merchant, but we want to acknowledge his seminal work and his inaugural lectureship. Today, we are here to commemorate a number of things. We are very happy to be able to introduce Bert Brunekreef, who's our 2021 John Peters lecturer. For those of you who have not had the opportunity to work with or know or read about some of Bert's accomplishments and his scholarly accomplishments, his academic work, and followed him, I'll give you sort of a brief summary. I could easily spend the next hour talking about Bert's accomplishments. He is an emeritus professor of environmental epidemiology at Utrecht University in the Netherlands. He, prior to that, had a successful career, academic research effort at Wageningen University, also in the Netherlands. He has been involved with and a participant of many large studies in Europe related to air pollution, allergy, and health. Is considered one of the world's preeminent air pollution epidemiologists. Has led a number of studies and been the principal investigator on studies funded here in the United States by the U.S. The Health Effects Institute. Has commented on or been a critical part of his work, has been critical in terms of establishing standards here in the United States under the EPA's Review on the Clean Air Act, of National Air Quality Standards, of the World Health Organization, and just have been an advisor really internationally in all manners of air quality work. As a researcher, he has authored or co-authored 600, more than 600 peer-reviewed articles in environmental epi and exposure. He's received a wide array of awards from a number of national, international, and university institutions. I won't list them all at this point, but I will note that he is well regarded sort of universally for his work and has not only been a counseled, a respected advisor to us in terms of learning about air pollution research and in guidance and mentorship, but has also trained a generation of new researchers to continue on in his work. So we're proud, we are honored to have Bert Brunekreef with us today. He will be talking today on a topic that he knows well, his perspective on the increasing search and understanding of ever and ever lower levels of exposure, eliciting untoward health effects. And so entitles his lecture Low Level Science. So at this point, I will stop sharing my screen, allow Bert to share his screen, and welcome Bert to us, and thank you for being with us today to share your thoughts.
Thanks for your kind introduction, Ed. Trying to share my screen. Share. That does it.
It was okay.
There it is.
Yes, we can see it.
That's good. I can see it myself, which is probably even more important. Ed, thanks very much for your kind introduction. It's a great pleasure and an honor for me to deliver the 2021 John Peters Lecture, which I call Low Level Science, and I'll explain that term in a minute more. I want to start with a tribute to John. John kindly invited me to become the chair of the International Advisory Board of the Children's Health Study in some year that I forgot exactly when. And this was great for me. You know, the Children's Health Study is a great study, and the meetings were always very nice with good science, good people. And the best part always came at the end of the meeting when John would invite some of us to his office or to his home to uncork some fabulous wines to share with us. And what I will do, I'm 9 hours ahead of you, as you probably know. So what I will do after my lecture and after the questions have been answered, I will pour myself a very good glass of wine and think about John and the Children's Health Study a little more. On to the lecture, low-level science. I'll spend most of my time talking about the science of effects of low-level pollution, low-level air pollution, that is. I'll also spend some time talking about the question whether our science, environmental epidemiology, is intrinsically low-level, low-quality, low certainty, question mark, as some people think it is. But let's discuss that in a minute. You're well used to studying low levels of air pollution in the Children's Health Study, and I'm going to start with some examples from your own work. This is Robert's paper from Thorax 2014, in which you see the distribution of NO2 concentrations at the residential address in different communities participating in the Children's Health Study. I've highlighted one, Santa Barbara, because that's the lowest community in terms of NO2 concentrations, and it's entirely below the World Health Organization air quality guideline. You probably know the EPA air quality standard for NO2 annual average is more than 50 ppb 100 micrograms per meter cube. You can see that the entire children's health study population was already by then below that standard, and it's important, of course, to ask the questions. Is that EPA standard adequate to protect public health, or isn't it? That's the whole question about low-level effects. Are the standards adequate to protect public health, or are they not? This is one panel from the same study, looking at the effects of NO2 on FEC, now separated for the different communities in the children's health study. You can see that Santa Barbara, which, as you recall, has had by far the lowest NO2 concentrations in this study, had an effect estimate for the relation between NO2 and FEC, which was certainly not smaller and sometimes larger than the effect estimates in the other cities. And the pooled estimate was actually a smaller effect than what was observed at the lowest concentrations in Santa Barbara. So a clear indication, and this is just one study, clear indication that something is going on at very low levels of NO2, or the mixture that it represents in these studies inevitably. Interestingly, the Federal Register of April 18, 2018, which promulgated the latest revision of the NO2 standard, concluded that that there is likely to be a causal relationship between long-term NO2 exposure and respiratory effects. At the same time, the text goes on to say that evidence does not call into question the adequacy of the public health protection provided by the current standards. And I've shown that the whole children's health study is well below the current annual average NO2 standard in the US. I was and have been to this very day been puzzled by the fact that EPA did not see any reason to reduce the annual average NO2 standard based on the evidence that was already available before the 2016 integrated science assessment was published. That's a reminder of the link between low-level studies and potential policy implications. And finally, another paper from your children's health study, also first authored by Robert Uhrman, looking at the percent change in lung function that might be achieved if you would reach hypothetical thresholds, 30 ppb or 20 ppb, and clearly suggesting that if you would be able to reduce NO2 to 20 ppb, and no more than that, which is about 40 micrograms per meter cube, you get a significant improvement in lung function in children in these settings. And this is a recent paper, and it continues, I think, to put pressure on the regulatory world to take these kinds of studies seriously and start thinking hard about further reductions of air pollution in order to improve public health. Now on to the current work that we're doing to study low-level effects of air pollution. I have the privilege of being the coordinator of the ongoing and almost finished ELAPSE study, which stands for Effects of Low-Level Air Pollution, a study in Europe. And it's funded by the Health Effects Institute. It's mentioned already by Ed in his introduction. And this is a study that is done in conjunction with two studies in North America, one in Canada with Mike Brower as the PI, and one in the United States with Francesco Dominici as the PI. The study in Europe covers some 28 million subjects, Canadian study about 9 million, and the US study is on the Medicare population of about 61 million subjects. These are very large studies. I won't talk about the North American studies, but I'll continue now with the European study and what it is showing so far. The Health Effects Institute, in one of his annual conferences, organized a group meeting for us. And at the meeting room, we were announced as the low-level investigators. So that's what we are, Mike Brower, Francesco Dominici, all of our colleagues. From now on, we are low-level investigators, just that you know it. The background is that associations between air pollution and health have been observed at low concentrations in exceedingly large numbers of studies. The objective of our study in Europe was investigate associations between long-term exposure to PM2.5 but also NO2, ozone, and black carbon, and natural and cause-specific mortality, but also the incidence of lung cancer and cardiovascular events, and we added some respiratory events to that in a later stage. The study has two parts. One is regular cohorts, and we pooled 8 of the original ESCAPE cohorts together with the Danish nurses cohort for a total population of almost 400,000 subjects participating in these 9 cohort studies. Then we had large administrative cohorts, as they are called, like the Medicare, but then different, from 7 countries in Europe for a total of almost 28 million subjects. We used the common codebook, harmonizing individual and area level variables between the cohorts. We had a central exposure assessment effort for all 4 pollutants at a 100 by 100 meter resolution, which is key in these kinds of studies, looking at small scale spatial contrasts in pollution. The pooled cohort, as I mentioned, consisted of 9 different cohorts. In Stockholm, Denmark, Copenhagen, we had 2 cohorts, 1 in the Netherlands, two cohorts in Germany, 1 in France, 1 in Austria, 1 in Italy. So those are the white dots on the map. Or some 400,000 subjects, as I mentioned. And all of these cohorts have extensive covariate information, which is what you would like to have in order to be able to adjust for suspected confounders. The administrative cohorts were located in Belgium, Denmark, Holland, England, Norway, Rome, and Switzerland. With the exception of Rome, these were all nationwide studies, with the exception of the English study, which is from a general practitioner database, which had actually a lot of individual covariate level information. These administrative databases do not have a lot of individual level covariate information, so we needed to deal with the problems that creates, as in studies in North America, which are also using these large administrative databases. The exposure assessment was based on a Europe-wide hybrid land use regression model. We used land use and road data, but we also used satellite observations and dispersion model estimates as additional predictors that produced maps like this of Europe for PM2.5. And the insert is the concentration gradients estimated for the city of Paris. And you can see that especially in the Po Valley area in Italy, the highest concentrations are still being observed or estimated in Europe. We were able to use hundreds and hundreds of monitoring stations from the so-called airbase system. The red dots are NO2 monitoring stations, the blue dots monitoring stations that measure both NO2 and PM2.5. We also utilized the more locally concentrated monitoring sites of the ESCAPE study, which was linked to a large number of cohorts in Europe, as you may recall. And there we had information on PM composition and black carbon as well. So we were able to build models of PM composition, which I won't talk about today, and black carbon based on the ESCAPE monitoring data, which I collected some 10 years ago in all of these areas in Europe that you can see on the map on the right-hand side of the slide. For the administrative cohorts, we used random effects meta-analyses to generate pooled effect estimates. Because they were analyzed separately, we could not pull the data from the administrative cohorts for privacy reasons. We did 2 pollutant models to figure out what happened to the effect estimates of one pollutant after adjusting for another. We had a series of detailed sensitivity analyses, which I will be able to show only a few of today. So some of the pooled cohort results first. Remember, these are 9 cohorts with intensive individual level covariate information. These are the distributions of the PM2.5 concentrations. You can see that the 4 cohorts in Stockholm, in the Stockholm area, are all well below the air quality guideline of the World Health Organization, well below the US EPA standards. Then we had different cohorts in Denmark, other countries that I've shown on the map, And you can see that there was a rather large range within and between cohorts of PM2.5 concentrations. Everything well below the EU limit value, which has no health meaning whatsoever, which has been recognized for a long time. And that's why most countries in Europe are trying to improve the situation, regardless of whether the EU limit value of 25 micrograms per meter cube is being breached or not. NO2, again, a large variation within and between cohorts. There's less of a situation with very low concentrations in Scandinavia because the Stockholm cohorts are all they have their own traffic sources. So that's the difference for NO2 is less than for PM2.5. You can see that a large that for most of the subjects, the concentrations estimated were well below the EU limit value, which is the same as the WHO air quality guideline of 40 micrograms per meter cube. In Europe, the European Environment Agency uses on recommendations of WHO also a 20 microgram per meter cube threshold for quantification of health impacts associated with NO2. So that's why the 20 micrograms per meter cube line is in the graph as well. As I mentioned, we had some 400,000 subjects in the population. Of those, some 325,000 had really full data on all covariates, 47,000 deaths, and more than 6 million person years of observations that we could work with in the analyses of the pooled cohort. These are the effect estimates for natural cause mortality and cardiovascular disease mortality. You can see there was a clearly significant increase in mortality for PM2.5, 1.13 per 5 micrograms per meter cube. For NO2, 1.09 per 10 micrograms per meter cube. For black carbon, 1.08 per unit. And then interestingly and a bit puzzling, a seemingly protective association with ozone. Same pattern for cardiovascular disease mortality, positive associations, clearly significant, PM2.5, NO2, and black carbon, and a seemingly protective association with ozone. This slide shows the effect of adjustment for different sets of confounders. Model 1 is the least adjusted model, only adjusting for age, sex, and calendar year of recruitment. Then model 3 had individual level confounders, as well as neighborhood income level confounders to deal with, to adjust for. You can see in the table, you go from the left to the right. There wasn't all that much difference between the fully adjusted effect estimate and the model 1 minimally adjusted effect estimate. So that showed that confounding was not a major issue in this analysis. This was true for all 4 pollutants, as you can see in the table. We had highly positive correlations between black carbon and NO2, not surprisingly, because they are primary traffic emissions. All but 3 of those correlations were higher than 0.7. We had fairly strongly negative associations between ozone and all 3 pollutants, varying a bit from place to place, but clearly negative associations between ozone and the other 3 pollutants. It's one example of the shape of the concentration response curves. That's of course important when you asking yourself the question, what happens at the low end of the exposure range? You can see for both PM2.5 and NO2, there was a monotonous increase in the hazard ratio with increasing concentrations, leveling off at the highest concentrations, where we basically had not much observations. So those estimates become very uncertain at the high end of the concentration range. The red lines reflect the air quality guideline again from the WHO and the EPA standard. And you can see that in this analysis, even though we didn't have too many observations below 10 micrograms per meter cube, there was clearly a strong increase in the effect estimates going from less than 5 micrograms per meter cube, 2.5 to 10 and beyond. NO2, the same story, almost everyone was below 40 micrograms per meter cube. You can see that starting from levels well below 10 micrograms per meter cube, there was an increase in the hazard ratio for NO2 and all-cause mortality. natural cause mortality as well. We did so-called subset analysis, censoring the population to levels with ever lower cutoff points. I've highlighted some results in yellow that show that if you restrict the analysis to folks having concentrations all below 15 micrograms per meter cube, still got a significant increase in risk. Same is true for below 12 and below 10, the risk is still increased, but the number of observations becomes very small. The effect estimate loses precision, as you can see from the much wider confidence interval. NO2, effect estimate was essentially unchanged. If you looked at the full data set or restricted to below 40, which is the air quality guideline, below 30 or even below 20. So even below 20 micrograms per meter cube, which is half the WHO air quality guideline, was a clear indication of a positive association between NO2 and natural cause mortality in the pooled cohort. Two pollutant models. If you look at PM2.5, the effect estimates were somewhat attenuated, but remained clearly significant after adjustment for the other three pollutants, which is the upper row of the table. NO2 pretty much unchanged, irrespective of which pollutant we adjusted for. Black carbon more or less disappeared after adjustment for NO2, which it was highly correlated, as I mentioned. For ozone, the effect estimates were not much changed. They were becoming somewhat larger, as you might expect, given the negative correlations between ozone and the other pollutants, but they still were suggestive of a seemingly protective effect after adjustment for the co-pollutants, which again is puzzling. We concentrated our exposure assessment to the year 2010, so that was the main analysis, partly because that's when we had the escape monitoring campaign. Of course, we realized that many of these cohorts were recruited well before then. We back extrapolated two different methods to the baseline exposure concentrations, and we showed that especially for PM2.5, the effect estimates were much smaller after going back to the baseline exposures, which is what most studies actually do. The effect was of the back extrapolation was much less clear for NO2 and black carbon, also not so very clear for ozone. For PM2.5, it's important to keep in mind that even though we planned this as a sensitivity analysis, these effect estimates are probably more realistic than the relatively high effect estimates that we had in the main model looking at 2010 exposures. One example of an additional analysis that we did looking at respiratory effects. This has actually been published late last year in the European Respiratory Journal already. An analysis was in cohorts in Denmark and Sweden only, which had these data available. And you can see that for asthma incidence among adults in these cohorts, the effect estimates were remaining positive and significant after a reduction of the analysis to level 2 folks with concentrations below 40, which was almost everybody, below 30, which was the large majority, and even below 20, the effect estimate was elevated, but no longer statistically significant because the number of observations became smaller. Just one example of a respiratory endpoint, morbidity endpoint on top of the mortality analysis that we showed. Ozone, a natural spine in an attempt to look at what this seemingly protective association really meant. You can see there's not a clear indication in this graph for something fishy going on in the shape of the concentration response curve. We do note that the range of exposures was very small, almost entirely between something like 75 and 95 or 100 micrograms per meter cube, which is a range which is much smaller than the range observed in the North American studies, where ozone tends to be positively associated with PM2.5 and not negatively, as we found in our European study. We did try something else, and that was restricting the ozone exposure estimate to dispersion model estimates only, so forgetting about the finer scale 100 by 100 meter spatial scale. But even at 50 by 50 kilometers or 10 by 10 kilometers, which is what the dispersion models give you, the effect estimate was still seemingly protective for natural cause mortality and other endpoints that we looked at. So at this point, we don't really have a clear explanation for the negative associations with ozone, except that we do note again that the correlation with the other pollutants was clearly negative. There may be an issue with measurement error. With measurement error in one or more of these pollutants, that means that the adjustment is not complete, and some of the effect estimates for ozone remain even after adjustment for all the pollutants. Administrative cohorts. Then we had 7 administrative cohorts: the complete population of Norway, a large population in England, complete population of Denmark, the Netherlands and Belgium, Switzerland, and the complete population of Rome. So these are the large numbers that we were able to work with. And these are the concentration distributions within and between cohorts. And now you can see that especially the Norwegian cohort was almost for almost 75% below the air quality guideline of the World Health Organization. You can see that everybody was, of course, below the EU limit value, and variations within and between cohorts, as you can see from the box plots in this graph. Same for NO2, where the within cohorts distributions tended to be wider, and the between cohort distribution related to the fact that NO2, as you all know, is a more locally generated pollutant. It's more related to local traffic than long-range transport, which is important for spatial distributions of PM2.5. Effect estimates from the pooled cohort, the administrative cohorts. This is now the meta-analysis of these 7 administrative cohorts. And again, showing clearly positive association with natural cause mortality, NO2, with black carbon. And again, a seemingly protective association with ozone. Cardiovascular mortality, same pattern as for all-cause mortality. Stroke, positive associations, but a little less clear than for cardiovascular disease mortality. So not reaching statistical significance for PM2.5 and black carbon. 3 more endpoints: respiratory mortality, clearly positive associations. Lung cancer mortality, clearly positive associations. COPD, almost significant for PM2.5 and significant again for NO2 and black carbon. Again, for all these 3 endpoints, again, the slightly negative association with ozone, as you can see from the lowest line in the table. A forest plot showing the differences between the individual administrative cohorts, showing that especially the Danish cohort had a much bigger effect estimate than the others. The average, the pooled effect estimate was clearly significant. It's the number that I showed in the previous table. Now to the same story, not much of an effect estimate in Belgium, the Belgian cohort, stronger in Denmark, and then with some variation in the other 5 cohorts, all leading to a clearly significant pooled effect estimate from the 7 studies. And I'd like to remind you again that 6 of these 7 studies had limited information on individual level covariates. So no data on smoking, diet, and BMI, for example, at the individual level. So we had to make do with area level socioeconomic status variables to try to tackle confounding in these cohorts. Some graphs from the Norwegian cohort, which, as you'll recall, had the lowest concentration levels, and you can see that nothing much going on at higher concentrations where the effect estimates become very uncertain. Below 10, almost linear increase in hazard ratios in the Norwegian cohort for PM2.5, starting well below 5 micrograms per meter cube. NO2, same story, starting well below 10 micrograms per meter cube. There was nothing much going on above 20 micrograms per meter cube in the Norwegian cohort for NO2. This is again natural cause mortality. Again, the subset analysis now is a much larger population, and showing that the effect estimates for PM2.5 pretty much remain the same with every restriction to below 15 micrograms per meter cube. Then they increased somewhat, and even below 10, and we were down to 4 cohorts out of the 7. It's 2 million subjects in the population still. There was still a significant increase in mortality in the meta-analyses of these remaining 4 cohorts. NO2, same story, with significant effect estimates if we restricted to below 40, below 30, below 20, still the same effect estimate by and large, but no longer statistically significant because the number of observations really became rather small, below 20 micrograms per meter cube. The pollutant models, now the situation was a bit different compared to the pooled cohort for PM2.5. Hazard ratios when adjusting for NO2 essentially reduced to unity. NO2, the effect estimates pretty much remained stable after adjustment for PM2.5, black carbon and ozone. So that's the one that came out as a winner, so to speak, in the meta-analysis of the administrative cohorts. Black carbon, more or less resistant against adjustment for PM2.5, but reduced to almost unity after adjustment for NO2. And here the effect estimates for ozone no longer reach statistical significance after adjustment for NO2, but also after adjustment for black carbon. So this is an indication, I think, that some negative confounding might be going on still when it comes to these surprisingly protective, seemingly protective associations with ozone. And I say seemingly because I don't think anyone would like to conclude it from now on that ozone is good for you based on these study results. We had a method which was developed by our Canadian counterparts to do indirect adjustment. I don't have time to explain exactly how it works, but you take associations between individual level confounders and air pollution based on surveys that are representative for the large administrative databases. And we had surveys like that in all of the 6 administrative cohorts, which did not have individual level covariates. And then there's a couple of tricks that you can do to arrive at indirectly adjusted hazard ratios, which then are seen as now sort of roundabout way to adjust for the individual level covariates like smoking, BMI, diet. You can see that the effect estimates change the main model to the indirect adjusted. Some of them go up, some of them go down. By and large, the effect estimates remained positively and significantly associated with PM2.5, is indirect adjustment. NO2, we did the same. And again, after indirect adjustment, the effect estimates all remained significant or even became significant, as in the case of Belgium. And the range of effect estimates actually became smaller. So these indirect adjustments apparently explain some of the heterogeneity, the effect estimates that we observed between the administrative cohorts without this kind of adjustments. That was interesting to note. Take-home messages from the ELAPSE study so far. The report is almost done, so hopefully it will be published in a few months' time. Long-term exposure to PM2.5, NO2, and black carbon was positively associated with mortality and morbidity in the pooled cohort and 7 large administrative cohorts. Hazard ratios for PM2.5 are somewhat larger in the pooled cohort with detailed individual confounder information than the administrative cohorts. And associations tended to remain at low to very low levels, which is below 10 micrograms per meter cube PM2.5 and below 20 micrograms per meter cube NO2. Yeah, this puzzling observation for ozone, which we can't quite explain. We do note that the range was much narrower in the European cohorts compared to the North American studies. We had negative correlations between ozone and the other pollutants in Europe, whereas they were positive in the North American studies. An adjustment for co-pollutants reduced but not completely removed negative associations. And we're looking into reasons for that more closely. And as I mentioned, measurement error might be an issue that's that was not completely addressed so far. This brings me to the end of the presentation on the ELAPSE study, and I have a couple more slides that go into an entirely different issue. So I will share with you, and then there will be still sufficient time left that we have until 10 o'clock my time, in 1 p.m. your time. Is that correct? Because the slides won't take more than another 15 minutes or so. Okay, low-level science. Is our science, environmental epidemiology, intrinsically low-level, low-quality, low certainty? Question mark. I'm asking this question because increasingly assessments are being asked of the overall quality, level, certainty, whatever you want to call it, of bodies of evidence. And these are typically meta-analytic effect estimates that we develop in support of environmental standards or guidelines and policy decisions. There's Cochrane, there's OHAD, there's GREAT, there's navigation, there's probably a bunch more other of these systems around that try to help you make these kind of assessments of the overall certainty of the evidence. But if you're not carefully looking at what these exactly are doing, you may come to, I think, wrong conclusions about how high the certainty of the evidence actually is. Example that I've been confronted with myself in detail is the revision of the air quality guidelines. Until the last revision in 2005, the air quality guidelines were based on narrative reviews, including toxicology, including chamber studies. And in 2014, WHO developed or published a handbook for guideline development that we are now expected to follow for each and every guideline that's being developed by WHO. It has many good things to it. It has a detailed protocol for formulating questions, for example. It's a detailed protocol for systematic reviews of the evidence. Then detailed protocol based on the GREAT system for assessing the evidence, and a detailed protocol to move from evidence to guidelines. I will focus on the GREAT assessment primarily because there's not enough time to look at the other issues. In the air quality guideline revision that we are still working on, it's almost done, but not completely yet. We eventually decided to modify the GREAT tool. GREAT stands for Grading of Recommendations, Assessment, Development, and Evaluation, because we felt it was not entirely suitable for working with environmental health issues. And the handbook for guideline development actually recognizes this with the highlighted part that the GREAT working group has not yet finalized methods for regarding environmental exposures and methods for assessing the quality of the evidence based on these things are still need to be developed, and they were still not developed when we started working on the air quality guidelines. So we had to find our own way through this. As per the WHO handbook, starting point for observational studies is actually low certainty. And that's because GREAT is very much developed to look at randomized controls trials as gold standard. And compared to that, the assessment is that observational studies, because of the limitations in the way they're able to deal with confounding, etc., have a starting point of low certainty. And there's 5 options to even downgrade further that low certainty: risk of bias, indirectness, inconsistency, imprecision, and publication bias. And there's 3 upgrade options: dose response, all plausible confounding away from 0, and large effect size. Important is that the system uses a one strike you're out approach, as I call it. That is, you do not get any upgrades when 1 or more downgrades are being applied. And in the original system, it's actually quite easy to earn a downgrade. And if you do that, and now you go from low certainty to very low certainty, there's no way you can earn your certainty back in this system, which is, I would say, dogmatic. There's a simple 4-point scale as the output: high, moderate, low, or very low certainty. And there's much reliance on statistical significance of tests for inconsistency, publication bias, etc., etc. When the evidence is low or very low certainty, recommendations in the systems are conditional at best. And a conditional recommendation, I think, is likely to be ignored in the policy process in most parts of the world as we know it. So it is very important to ask ourselves the question, now, how certain are we that if we arrive at a low certainty or very low certainty verdict for our bodies of evidence, how certain are we that this is a correct assessment? We developed, after much discussion, a risk of bias assessment tool for the systematic reviews of informing the air quality guidelines. It's been published. This tool is by no means perfect, is my own personal point of view, but it resulted from rather long discussions between two consultants from the great collaborations, which were hired by WHO to help us, and the subject matter experts in the guideline development group. So even though this is published and I noticed already is being used by some other groups that are doing systematic reviews, it has a number of caveats which are actually voiced clearly in the tool. So if you are going to use it, I would recommend to read it very carefully from the beginning to the end before doing the more administrative parts of the tool. We adapted the grades in the air quality guideline development group because we felt after long discussions that the validity of the grade tools is not well documented for environmental health. We found out, for example, that the risk of bias tool that we developed after much discussion actually did not predict bias in the body of evidence. We noticed that heterogeneity is common and often explainable in our line of work. And we especially noticed that funnel plot asymmetry, which is one tool to estimate the likelihood of publication bias, is not the same as publication bias. Tests for funnel plot asymmetry measure funnel plot asymmetry, and that may or may not be an indication for publication bias. And we decided to focus more on multi-center studies, which are not likely to suffer much from publication bias for that reason. So the great document, which has been published as well by now as an appendix to systematic reviews that were published also, has additional guidance to help you come to more reasonable decisions we found about the certainty of the evidence. We also, in our adaptation, we decided to start at moderate certainty and not at low certainty. And we decided to accept upgrades in the presence of downgrades in view of the uncertain validity of the downgrade instruments for the grade tools. One example of how the tool failed to predict bias comparing studies at low to moderate risk of bias for PM 2.5 and mortality. The effect estimate was 1.09, 18 studies. And we compare that to all studies, so including the high risk of bias studies. We got an effect estimate which was essentially the same, 1.08. NO2 and long-term mortality. Studies at low or moderate risk of bias had an effect estimate of 1.03. That was exactly the same as studies at high risk of bias. So this tool makes no distinction whatsoever between the effect estimates of studies in one or the other category, which makes you wonder what exactly you're doing when you're applying a tool like this to come to an assessment of the certainty of a body of evidence. A few words about publication bias. I assume many of you are familiar with the idea of a funnel plot. You plot the effect estimates in a body of evidence against the effect estimates on the x-axis against the standard error. The idea being that small studies which are cheap are more likely to be published when they are positive than when they are negative, and that you need to focus more on the studies with the lower standard errors, the higher precision studies. And the asymmetric example of the funnel plot is shown on the right-hand side of the graph. Now this, if you look at these hypothetical examples of funnel plots and compare those to the funnel plots that we produced in the air quality guidelines, this is the one for NO2 and all-cause mortality. you can see that there's not a majority of studies which are small. It's high standard error, but almost all studies are big and have a small standard error cluster at the top of the line. And if you are faced with a funnel plot like this, visual inspections and also the Agar test do not mean very much. Another example for daily mortality in PM2.5. This is where the Agar test that can be applied to the funnel plot suggests that a very significant deviation. So the initial assessment was that this was a downgrade because of publication bias. Then we took a closer look at this particular funnel plot and decided to remove all 7 studies with the largest standard error. So the studies which would likely be responsible for the funnel plot asymmetry. This Agar test remains completely significant. And what now became visible because the scale changed was that there were 3 studies which were very highly, with very small standard errors, so very big studies which were essentially responsible for the significance of the Agar test. We removed the big studies instead of the large studies. The Agar test became non-significant, and this is the remaining funnel plots. So you can see that it was essentially measuring heterogeneity and not publication bias. And heterogeneity, if we go back to this slide again, was explained because all 3 studies were from China, where the concentrations were much higher than in the other studies. And in 2 of those 3 studies, actually, the investigators demonstrated that in different ranges that over the PM2 concentrations that they studied, the effect estimates were higher in the low part of the range and in the high part of the range. So completely explaining what the heterogeneity was that caused this significance of the Agar test in the funnel plot analysis. And this is from a recent paper in the New England Journal looking at PM2.5 and short-term mortality from time series studies in no fewer than 652 cities. You can see from this graph that there's a clear indication that the effect estimates are smaller at higher concentrations, which is where the Chinese studies were in the previous graph, and much larger at the low end of the concentration range, which is where the European and the American studies North American studies tend to be. Finally, a few words about 3 meta-analysis systematic reviews which came out in less than a year's time. The upper one was the one produced for the WHO Air Quality Guideline revision. And there was one from David Steep and his colleagues in PLOS One, and another one in Science of the Total Environment, also published this year. All 3 of these systematic reviews were done by, I would call, reputable groups of scientists. So these were, if you look to the list of authors, you can clearly see senior authors well known to us. So these are not just attempts by junior investigators, which you sometimes see in the literature at systematic reviews. And what I found interesting is if you looked at the main tables which produce the overall effect estimates, and if we go back one slide, see that the overall effect estimates were pretty much the same from these 3 meta-analyses. So that's a good bottom line, I guess. But then if you look at the details of these meta-analyses, you can see that of the 24 studies included in the main table of the WHO exercise, only 18 studies were listed in Steep's table, only 16 in the Wang's table. If you looked at the 32 studies in the main analysis from Steep, only 20 were identical to the WHO exercise, 17 in the Wang exercise, 28 studies in the main table from the Wang, 17 were identical in the other 2 meta-analyses. So despite the fact that these are using this detailed protocols for extracting the literature, you see that in the end, the tables producing the final results are not anywhere nearly the same, even though these 3 systematic reviews were published within 1 year from each other. Even more striking was the difference when you looked at when you zoom in on the agreement in the risk of bias from confounding. The WHO study had 24 studies, as I mentioned, had 23 in common with the navigation, with the Steep publication when it came to studies that were looked at from a risk of bias point of view. Of those 23, the assessment was the same for 0 of the publications. For the 17 which were used in the Wang study, only 3 the assessment was the same. So even though in the WHO study and the Wang study, the exact same tool for risk of bias assessment was used, the outcome was completely different. That's important to keep in mind, and it speaks to the, I would say, the incomplete science that we, or if you want to call it science, that you're using to come to conclusions from systematic reviews. I'll skip this one because I will come to an end of my presentation. Take-home messages for this assess uncertainty, and again, this is very much in development, I would say. In many of these tools, grades, Cochrane, OHAP, navigation, you name it, assessing the certainty, I think, is thwarted by the RCT paradigm, as I call it. The kind of work we do is not RCTs. It doesn't lend itself to RCTs. And it doesn't make much sense, I think, to judge them based on, by looking at them as if they were RCTs. Current assessment methods used within GRADE, which we used for WHO, have many limitations, and especially those for risk of bias, heterogeneity, and publication bias require very careful consideration before you can use them properly to come to an assessment. And for all of these things, we came to the conclusion that very detailed subject matter expertise is mandatory. So the final conclusion is, don't try this at home. Thank you for your attention. Stop the share.
So thank you.
I realize I may have buried you under a lot of information, but I made it in time.
Not at all. Thank you very much for a provocative and thoughtful commentary on a number of data sets and perspectives of how to look at them. The floor is open now for discussions. I would just ask, or questions. I would just ask that either you raise your hand or wave wildly. We have about 50 people or more on the call, and so trying to keep it in some sort of organized way would be the challenge. So who would like to start with the question, please? You're clear to go ahead.
Maria has her hand up, I think.
Okay, please.
Hi, can I go ahead?
Yes.
Okay. Hi, Dr. Ward. Yeah, this is really fantastic presentation. Yeah. And I'm Mustafidur Rahman. I'm a postdoc here working with Dr. Rob McConnell. So I have a question about the exposure response curve. So we have seen in long-term air pollution study and both in short-term air pollution study, the curve is leveling off at the high concentration level. So is that only because of there are fewer number of observation for high concentration day, or there is other things like difference in composition in low concentration and high concentration, different in PM 2.5 composition in high concentration and in low concentration?
Well, that's a good question. You're looking at different populations exposed at different levels of exposure. So that may be one reason for differences. Certainly in some of the examples that I showed, there is lack of information at the higher levels. So the lines become very uncertain and not really interpretable, I think. The example I showed from the 652 city study from the New England Journal came out 2 years ago. Now it has data from every part of the concentration range enough to make an assessment. I think there could be a saturation phenomena going on. If you go from 5 to 10, that's a doubling of the concentration, and if you go from 105 to 110, that's much less of a difference. It's the same difference in absolute terms, but relatively speaking, it's much less of a difference. So that may play a role as well. I don't think it's completely explained, but it's observed all the time.
Yeah, observed all the time. Yeah, so in both exposure curve, it is clear that the effect is higher in the low concentration days. So, and we know that especially in the low concentration or in our baseline concentration day, that is mainly dominated by the regular pollution source. It could be traffic, nearby traffic, or local industries. So with knowing that, so why we are not regulating the air quality policy based on the source? Like we are still relying on PM 2.5 mass.
Well, that's a policy question, I guess. In all of these studies, if you zoom in on the really low end of the exposure response curve, you're no longer looking at urban populations, but you're looking at rural populations, I think. If you look at the Canadian data, for example, you're not looking at Ontario, you're looking at other parts of Canada. If you look at the North American studies, you're not looking at the big cities on the east or the west coast, you're looking at rural sites in North America. The same is true in the European studies. If you look at Norway, the low concentrations, they're not in Oslo, but they're in the rural parts of the country. Sources there when it comes to PM 2.5 are, I would argue, still mostly long-range transport. NO2, it's probably still local traffic, so you may be right that traffic is the source to worry about mostly when it comes to NO2. The long-range transport, PM 2.5, has a lot of secondary particles in it, ammonium nitrates, ammonium sulfates, and I'm not sure about the United States, but in Europe, definitely there's a huge contribution of ammonia emissions from agriculture to the secondary PM formation. So there's lots of simulations that have shown that if you want to do something about PM 2.5 mass concentrations in big parts of Europe, the first source to tackle is ammonia from agriculture.
Thank you.
Thank you.
Other questions? Go ahead, Bill. Yeah, go ahead, Bill. You're on mute.
Can you hear me now?
Yes, go ahead.
Yeah.
Thank you. Sorry about that. It said the host muted me. I must have made noise unconsciously. Anyway, yeah. As the older people among you already know, I tend to be obsessed with ozone, which toxicologically or in human exposure studies has huge short-term effects, at least compared to anything else. But I'm wondering if Bert just mentioned long-range transport in Europe of particles. Is that also, or does that have anything to do with the apparent but probably not real protective effect of ozone? Or is it somehow that high NO2 due to urban traffic is driving down ozone?
Well, that's what we looked at in our two pollutant models. But those did not completely take away the negative ozone coefficient. So it remains puzzling, but I do think that there could be an issue of measurement error in some of these pollutants, which mean that you can't completely control for the effects that you're referring to. In the Canadian study, there is also a reduction, or there are also, I should not say also, but there is a reduction of the PM 2.5 effect estimate to almost unity after adjustment for oxidants, which is the combination of NO2 and ozone. They find that if you stratify by in tertiles of the oxidant concentration, that has an effect modification on the PM 2.5 effect. The PM 2.5 effect seems to be restricted to areas with the highest oxidant concentrations. And that's something we're still exploring in the European study. We haven't done that so far, but we have some additional funding from HEI to look at specifically these questions that cut across the three main studies that HEI is funding at the moment. But any good idea that for further analysis that we could do to dig into this more would be very welcome, Bill. And I know that you've been obsessed with ozone for a long time. So.
Yeah, I don't have any good ideas except, do you have any specific hypotheses or speculations about the measurement errors you mentioned? If you go back 40 years or more, a few of us can remember was very clear when you had a wet chemical ambient pollution analyzers, we used to call them. You could get serious interferences of ozone or in whatever non-oxidant or
yeah, we don't use that kind of data from way back. So the models were all built on relatively recent monitoring data from the year 2010 and later. And some of them were extrapolated back based on modeling modeling exercises. So we were not using monitoring data that go back 40 or 50 years, which suffer from the problems that may suffer from the problems that you're mentioning.
So as far as the analytical chemists are concerned, the instruments available in the last few decades are still believed to be fairly robust to interference is one thing from another. So it's not easily identifiable as a monitoring instrument problem, this conundrum.
Wouldn't be able to say much about it.
Let's see if we can squeeze in one more question. Yeah, Rob, you have a question?
Yeah, so I have a question about ozone also. Do you have, are there locations where you don't have inverse correlations between NO2 and ozone so that you could look at ozone independently and maybe the inverse effect would go away? And maybe
Yeah,
I got a related question, but go ahead.
Yeah, that's an interesting thought. As I mentioned in one slide, we did look at larger scale ozone models, spatial models, to get rid of the, let's say, near roadway negative correlations between ozone and the other pollutants that we all know exist. That didn't really solve the problem. So looking in the data for areas or countries where these correlations are not as negative might be an issue, but I must say that in the administrative cohorts, which were located in 7 different countries, as you recall, each and every one had negative correlations between ozone and the other metrics.
There might be within the they're big countries.
Yeah,
within the cohort.
That's an interesting thought. You know, we could maybe kick out the biggest cities from the analysis and see what happens, but we haven't. So that's an interesting thought. I'll keep that in mind.
And the other question also about ozone is, you know, about misclassification of exposure. And I think, yeah, we think of ozone as a regional pollutant and that we don't have a lot of variability in exposure within areas. But in fact, I think ozone is maybe the worst classified exposure because people spend so much time indoors, and indoors, it doesn't really matter what the outdoor ozone concentration is. So if the exposure to ozone is really bad, the misclassification is large for ozone, and there's some misclassification for NO2, this is not well thought out, but would you expect to see this pattern of effects? I mean, if you have essentially
Well,
very bad exposure assessment for ozone and some misclassification for NO2, would you expect to see an inverse effect?
that's why we restricted most of the analyses for ozone to the warm season. This is a little less of a problem. I do appreciate that ozone is difficult to characterize for all the reasons that you mentioned. In the warm season, the spatial contrasts are higher, so and also people spend more time outdoors. So that's why, and that's typical for much of the ozone epidemiology, that it focuses on warm season rather than annual average concentrations. See, Mike Jarrett is on the call, so he has done some of this work as well, so he may have some ideas. But it's puzzling, and we keep looking for good ideas, and looking within countries is certainly something that we haven't really considered so far. We may still be able to do that while the analysis team is still active.
Okay, thank you. One more question we might be able to squeeze in the remaining minute? Yeah, Mike, go ahead. Welcome. Hi, you're on mute.
Great talk as usual. Really enjoyed that. We did find evidence in the ACS cohort that there was a threshold below 35 parts per billion, so about 70. So it's possible that a lot of your cohorts are really below the threshold where there's going to be significant effects because of the distribution. Also, it's very latitudinally dependent in Europe, so it's mostly in Southern Europe that you have the high ozone exposure, so you might want to look at it there if you haven't. And then also ozone is always bound up, at least in North America, with a lot of protective effects for socioeconomic status. So you may want to look at this by different levels of temperature and different levels of socioeconomic status. I think it's going to be important to parse that out because it is a perplexing effect.
Yeah, the one graph that I showed most of the concentrations being between 80 and 100 micrograms per meter cube. So that would be between 40 and 50 ppb. I don't recall what the concentration range was in Norway, for example, but we have those data and we have the graphs all available in the report. So I'll look into those more closely and see whether we can find some hint of things to do.
Yeah, I'll send you a few follow-up thoughts.
Okay.
Thank you for the talk.
Yeah, thank you very much, Bert, for the interesting talk, provocative talk, stimulating talk. Thank you all for attending. We've run out of time. Unfortunately, this has been recorded, so you can check back with our center website and view this, see this, and tell your colleagues about it. We'll take a little break during the summer for our center seminar series and resume in the fall again. So we'll look forward to seeing you back. Thank you all. Thank you, Dr. Brunekreef, for sharing with us your thoughts and for helping you to now have that glass of wine and going into your weekend.
Yeah, I certainly will. Thanks again for inviting me. It was a great pleasure, and to see so many of the familiar faces again. So that was great. Thanks for having me.
Yes, be well and take care. Thank you all.
Thank you, everyone.